All right. Good afternoon, everyone.
Good
Okay,
afternoon.
thank you. Want to get you guys a little involved and at least awake when we start. So, for a second, continuing to be involved here, I want you to think back to maybe some of your favorite cartoons when you were a kid. One of my favorites was Dexter's Laboratory. Probably all of us 90s kids remember it. And I enjoyed Dexter's Lab in particular because I loved all the amazing science and the unbelievable experiments that Dexter was able to do. And as I've progressed into engineering and into my adult life, I've continued to love this science that we can look at it, we can explain it, but the results seem almost unbelievable. And so what I'd like to talk to you all about today is one of those types of technology which yields unbelievable results. And we're going to look at how it works. And that technology is known as LiDAR, which stands for Light Detection and Ranging. So in a nutshell, what LiDAR is it's very similar to things you may be a little bit more familiar with, things like sonar or radar, which are remote methods of imaging or mapping the world around us. Sonar uses sound. You can think of like a bat using echolocation, something like that. Or radar, which is often used in military applications, uses radio waves. What LiDAR does is it uses light waves. So to start out, I want to take a look at those light waves and the type of light that LiDAR systems use. And that's going to be lasers. So I'm not going to go through an extensive explanation of how lasers work because this is a process speech about LiDAR, not lasers. But simply put, you have some type of a medium here. Originally, actually, in the first ever laser, it was ruby. That's why that's red. But it just has to be some type of excitable medium. And a flash tube, or like basically a really bright light, goes off and excites the atoms, which release photons. And you can see in this diagram, you've got a mirrored surface on one side and a partially mirrored surface on the other. So as the photons are emitted, they'll bounce off the mirrors. The ones that aren't all oriented in the same direction will bounce off into space. And those that are oriented in the same direction get caught bouncing back and forth between the mirrors. And depending on the design of the laser, that's either a partially mirrored surface, so that some of the photons can travel out through that side of the laser column, I guess. Or there's sometimes a small hole, so that some of the photons can escape. And the result is a very directed and omnidirectional beam of high energy, powerful light. And this is very important as we look at what a LiDAR system does with this light, or with this laser. So what a LiDAR system does, and here we're using the example of one used from an airplane, is the LiDAR system scans back and forth with a laser over whatever's being mapped. In this example here, it's a city. Actually, it looks kind of like Glassboro the way it's set up. But that being said, it scans back and forth. And this laser beam goes out and sweeps the area. I kind of think of it like, you've got a professor that's walking around during an exam, looking around and sweeping the area, looking for students that might be cheating. But instead of sweeping students, what the LiDAR system is doing is using lasers to detect information about what's in front of it, below it, depending on the orientation of the system. So when a number of laser pulses are given off, and this is going to be probably in the magnitude of thousands of laser pulses per second. And once the laser pulses are given off, they then bounce back to the system, to a receiver. And so this image here kind of does a good job of showing that. A laser bounces down as a pulse, and then it returns to the LiDAR unit. And a timer is attached to this to time each individual pulse and return, and based on that, useful information can be calculated. As shown in this little equation down here, we can check our units as well, and we can see that this does work out. So you have your travel time for the pulse to leave the LiDAR unit and then return to it, times the speed of light, since we're using light here as what's traveling, and then you divide it by 2 since there's a travel down and then one back. If you cancel your units, you end up with distance in meters or miles, depending on your choice for your constant c, speed of light. And that distance is something that tells the LiDAR system how far away is this object. And remember, it's calculating and recording thousands of these distance calculations as it goes around and scans the area in front of it. So we have one set of data points here that give us how far away are things in front of us. But it's hard for the system to necessarily do anything useful with this data unless that data is oriented in space. So in order to orient the data points in space, a LiDAR system uses two different devices in particular as a part of the system. The first of these is a global positioning system, GPS. We're all very familiar with it, using it to drive places in our cars, get to Wawa, or it can be used in much, well, I don't know how important you consider your Wawa, but maybe more important applications, things, military usage or government usage, things like that. And for the LiDAR system, basically GPS works off a system of satellites and can triangulate your coordinates on Earth. So if the LiDAR system now knows where it is on Earth, not only does it know how far away something is, but then, okay, I'm at this coordinate point XYZ, and now this item that I'm scanning is so far away from me, let's say 10 meters away from me. It can simply calculate, a shift of its point to that point and have a spatially oriented data point for what it has scanned with the lasers. And then, particularly in use with airplanes, LiDAR on airplanes, we have something called an inertial, hang on, I wrote it down. Yeah, IMU, it's an inertial movement unit, measurement unit, inertial measurement unit. And what this does is it acts very similarly to the gyroscopes and on your phone, the gyroscopes and the accelerometers. So when you use your phone to go running, for example, and it's able to see by how the phone moves what your stride is, it's doing something very similar, measuring angles and measuring the angular changes in the orientation of the LiDAR unit. And this can be used to account for any sort of abnormalities in data when mapping it later. So we now have data points for distance data points from the LiDAR system using it as a reference point. We can orient it in space with the GPS, and we can account for any abnormalities due to maybe shift or change or turbulence in the LiDAR system using the IMU. So now we can put everything together, and there are onboard computers in the LiDAR system, and these combine data, making a mapping. Basically the same way that you in your algebra or your calculus class, you would go into a Cartesian plane and plot a point, 2, 3, or whatever. It can go through and do a much more complicated version of that to map a three-dimensional image based off of all these oriented data points in space. And the way I kind of like to think of it is like the world's most complicated light bright. So you have your light bright, and whatever, let's say I'm trying to draw a picture of an apple. So I have all these individual data points, or the pegs that you push into the light bright. And I put one in, that's one data point that I have. Then I orient them based on what I see and I'm trying to draw. And over time, all the data points come together in order to make a complete image. And so I wanted to just show off a couple of actual images recorded by LiDAR systems. So this first one here is of a mountainside in Montana. This is from a LiDAR company called Blackmore Sensors and Analytics that develop LiDAR systems. And they went out and they took an image at night using LiDAR of Big Sky Ski Resort, for those of you that may be familiar with the skiing out west. And then this image is of vegetation, of a tree actually, from the National Ecological Observatory Network. And they do a lot of work with LiDAR to record vegetation mapping and the effects on forests by different things based on how much vegetation is still there. So kind of to wrap up here, we've looked at two quick examples of applications of LiDAR. Here in topographical mapping, and that was actually one of the earliest uses of LiDAR to map terrain, and then also in vegetation mapping for environmental impacts. But example of application of LiDAR is in autonomous driving. This is, again, from Blackmore Analytics and Sensors, and they've been pairing with BMW and with Toyota to develop autonomous driving technologies where the car can actually see using LiDAR and drive accordingly. So, wrapping up here, as futuristic technologies become more fact and less fiction, it's both interesting and important to know not only how they work, but how they can apply to our lives and what they're being used for. Thank you.